Okay, so we are going to learn section 4.1 in this video. So this is taking derivatives and just looking at them in more of a real world context. So still a lot of the same stuff we do with derivatives, but kind of looking at it in actual like word problems that have meaning to them. Okay, so if I asked you guys to look at this graph, the line is blue on canvas. If it's online, on paper, it obviously looks black, but that is the tangent line that goes through the point 1, 0, the tangent line to f of x through the point 1, 0, and it is known that the derivative at 1 is 3. Interpret the meaning of the statement. So a lot of the time, what we've been talking about lately is that we know that that means that the tangent line at x equals 1 has a slope of 3. So we could say the slope of the tangent line to f of x at x equals 3. I'm sorry, at x equals 1, my fault, at x equals 1 is 3, right? It's kind of how we've been interpreting it so far, which is correct. That's not incorrect. But what we can also say that has a little bit more real world context, is kind of how what we're going to be working with today, is we could also say that the rate of change, because we know rate of change, derivative, slope, they all mean the same thing. Sometimes you're going to say derivative, sometimes you're going to say slope of the tangent line, sometimes you're going to say rate of change of the function. Okay, so the rate of change of our function, f of x, at specifically x equals 1 is 3. Okay, this is kind of more of the gist of what we're going to be talking about today. We're going to be talking about derivatives being rates of change, as opposed to it just being the slope of the tangent line. Slope of the tangent line is a little bit more in regards to like a graph. But we're going to be talking about kind of real world situations in which we're going to refer to the derivative as the rate of change of our function. Okay, rate of change, slope of the tangent line, derivative, all the same thing. They all mean the same thing. Okay. So it says, we have been studying derivatives, including differentiation rules and meanings of derivatives graphically. However, the problems we've been working with have been without context, don't really have a real world application. Now we will see examples of functions that do have context, real world meaning. When functions have real world context, then the derivative will also take on real world context. So let's take a look at some of these notes they have for you. In real world context, we rarely use x and y. Most of the time, we're going to use t for our x because we're going to do things with respect to time, like miles per hour, feet per minute, meters per second, things like that. So a lot of times the x that we use is going to be time. Okay, in contextual problems, derivatives have units, and it's going to be unit of the y over unit of the x. Like I just said, meters per second, feet per minute, things like that. So like miles per hour, feet per minute, so forth and so on. Most of the time, the x is going to be a time, hours, minutes, seconds, whatever that may be. And, then whatever it is that they're talking, it might be people per hour. It just depends on what it is. In a real world context, derivative is a rate. Rate is equivalent to a slope. Okay. And derivatives are still instantaneous, meaning they occur at a specific instance. So when you first learned derivatives, you learned like we took the picture on the roller coaster at that specific time, not the average from this time to this time, but what is the speed at that specific moment? This is the same thing. It's still at a specific moment. Okay. So rates mean the rate of change of this, instantaneous at the specific time. And here's our units. It's going to be like miles per hour, feet per second, so forth and so on. Okay. All right, moving on to the back. Here is a table, and it is in regard to the height of a sunflower in inches, which is measured over the course of 7 weeks. So you have a table for like at this many weeks, our sunflower was this tall, this many inches tall. Use the table above to estimate h prime of 2 and include the units of measure. So h prime of 2, it's important that you recognize, like, what does that mean? What is it referring to? That means our rate of change in the height of the sunflower, specifically at time 2 weeks. Okay, that's what they're asking you to find. They're asking you to find the rate of the change in the height of the sunflower at time 2. So how fast is it growing at specifically time 2 weeks? This many inches per week. That's what we're looking for. Okay, because our units are inches and weeks. You don't have 2 on this chart. You don't have 2 weeks on this chart. What you do have is the 2 things that surround 2 weeks, which is week 1, it's 7 inches tall, and week 3, it's 25 inches tall. We're going to use those 2 as if they're 2 points, 1, 7, and 3, 25, to estimate our slope or our rate of change at the point right in between, which is 2. So we're just going to do y minus y over x minus x. 25 minus 7 is 18 over 2 is 9. So it looks like the estimated rate of change at 2 is 9, but 9 what? Every time you have a problem that's in context, you have to include a unit. So that means that it's growing approximately 9 inches per week at time 2. Okay. At 2 weeks, it is growing at approximately 9 inches per week. All right, moving on to the next one. Very similar. You've got time, but in this one, you have a rate. You have the number of cars that are entering the parking lot of a grocery store T hours after it's open is changing at a rate modeled by C prime. So C prime is the rate of change in the cars per hour that are entering the parking lot. So that means it's going, it's 28 cars per hour at time 0, 65 cars per hour. Cars per hour is already a rate. Okay. It's asking you to find C double prime. Okay. Which means the rate of change of the rate of change. So we're finding the derivative of the derivative. We're still going to do the same thing, just like up here. You didn't find, this wasn't H prime. Sorry, this wasn't H prime, but you did height, you did the rate of change of the height to find H prime. Down here, you don't have C double prime, but we're going to do the rate of change of C prime, and that'll give us C double prime. Okay, so just like the last one, we don't have 6. 6 would fall right here in between 5 and 7. So we're going to use these 2 pieces, and we're going to do C prime minus C prime over time minus time, which will give us C double prime. That's going to be the rate of change of C prime, right? So that's going to be 54 minus 92 over 7 minus 5, which is negative 38 over 2, or negative 19. And our unit, the top, this already is cars per hour. I'm not going to write it like that. I'm going to say cars per hour. And then we're doing that per time, which is another hour, because this is already cars per hour per hour. So our Y value, if you will, is already cars per hour, and it's always Y over X. So change in Y over change in X. So you can write cars per hour, or you can write negative 19 cars per hour squared. You guys are usually pretty good with units, even like this kind of like double unit, because of chemistry. Chemistry is very helpful for y'all in understanding your units and how your units work. So hopefully that makes sense. If not, talk to me later. Okay. All right. Interpreting a derivative in context. You have to be very specific on how you're going to answer your question. Okay. And this is what this box is trying to teach you. You've got to include what the function is modeling in words. Then you got to make sure you include units. Then you've got to make sure you say you're clear that this is a specific rate of change at time this. It's always at a specific time. And then include the word rate in your sentence. Okay. So interpret the meaning of your answer. It's going to bleed over from example 1. This is the one they're talking about. So example 1, interpret the meaning of your answer. That means that this is technically what your answer should look like. Top of the next page. They've left you a box to fill in. Okay. So what are we talking about? What was example? Example 1 was the one about the sunflower. So we were talking about the height of the sunflower. So the height of the sunflower is either increasing or decreasing. If it's positive, it's increasing. If it's negative, it's decreasing. So ours was growing, right? So the height is increasing at a rate of, what was it, 9 inches per week at specifically time 2 weeks. Don't say time 2, to what? Could be seconds, could be minutes, could be hours. It's weeks. Okay, so these are the pieces that you need to have. You need to talk about, what am I talking about? What is growing or shrinking? Is it increasing or decreasing? And that depends on whether it's positive or negative. How much is it increasing or decreasing by with your unit? And at specifically what time, including your unit. Okay, if you don't include all of those things, especially in a free response problem, you might not get all the credit for that free response problem. Okay, so they're very specific on how they want your answers for things. Okay, all right, let's move on. So here's our next word problem. A factory produces delicious cans of corn for the typical corn enthusiast. One particular machine is notorious for packaging cans of corn at impressive speeds. The amount of cans this machine has packaged after T seconds is modeled by this differentiable function. So right now, you've got at this many seconds, it has packaged this many cans. Okay, it's asking us to approximate C prime of 1. Using the correct units, interpret the meaning of the value in the context of this problem. So we're finding C prime of 1, and then we're saying, like the box above, we're going to write a sentence saying what it means. Okay, so C prime of 1, we don't have a 1 on this table, but it would fall right here in between 1 and 2. I'm sorry, 0 and 2. So we're going to use these 2 points, and we're going to do slope because that's what a derivative is, right? So 52 minus 16 over 16 minus 0. That's going to be 36 over, it's not 16 minus 0. That's dumb. 2 minus 0, so sorry. 36 over 2 is 18. So C prime of 1 is 18, and we need a unit. It's going to be Y over X, so cans per second. So there's the first part of my problem. Now I have to write a sentence in with all of those pieces that they asked for in the box above. Okay, so the amount of cans packaged it's positive, right? So it is increasing at a rate of 18 cans per second at specifically time 1 second. Okay, so we talked about, what are we talking about? Amount of cans. Is it increasing or decreasing? Increasing because it's positive. At this rate with my unit, 18 cans per second. At this time with my unit, time equals 1 second. Okay. All right, let's go to the example 5. Example 5 says, at the end of a football game, this one doesn't have a table. Everything else we had so far has a table. This one doesn't give us a table. This one gives us an equation. Okay. Fans begin to exit the stadium. For 0 to 40 in time, which is minutes, it tells you that right here. From 0 to 40 minutes, the number of fans that have exited the stadium can be modeled by this function. Find f prime of 8. Okay, listen. Well, that's quite the little equation you got there. I don't want to find that by hand. It is most likely that this would be on the calculator section. We're going to assume that it is. Okay, so we need to go find that derivative in our calculator. You've done that before. So remember that you go to math and you press NDeriv and you're going to enter this equation. Make sure you put parentheses around the bottom and then comma the number 8 because that is what you're plugging in. Okay, or if you have a newer calculator, it'll give you like at x equals and you'll fill in the box with the number 8. Okay, either way, you're going to use your calculator to find the derivative of this function at x equals 8. So you're going to find f prime of 8. Okay, f prime of 8, when you put it in your calculator, you should get 265.5902-ish, right? So then we're going to not only find it, but we're going to answer the question the way that they have asked us to answer all questions. Okay, so that means the number of fans. Oh, I didn't put a unit. Hold on. Fix unit. It is people per minute. Fans per minute. Okay. So what does that mean? That means the number of fans that have exited the stadium and then you have to say if it's increasing or decreasing. It's positive, so it's increasing at a rate of 265.590 because we only round to 3 fans per minute or people per minute at specifically time 8 minutes. Okay. Nice thing about videos is you can pause, rewind, do whatever you need to do. So please feel free to do so. I'm going to move on to example 6. So a lot of them, you've been given an XY chart. That last one, you were only given an equation. And this bottom one, you're given a graph. Okay, so let's read what it stands for. From time 0 to time 10, the rate that people are getting on an escalator in people per second, so that's our rate, is modeled by the function p. So this is already your rate. Okay, where t is measured in seconds. So this is your rate in people per second. And that's confusing because a lot of the times you don't have a given rate, right? You're given like the amount of people, but this is actually a rate. So we're using the graph to find p prime of 8. P prime of 8 on a p graph. That means we're going to 8. We're going to this spot on 8, and we are finding its slope. So its slope is down 1, right 2. So that means that your slope at 8 is negative 1/2. So there's my slope at 8. And then I'm using that to interpret the problem and write my sentence. Okay, so what am I finding? I am finding p prime of 8. So if p is already the rate that people are getting off on an escalator, then I'm finding the rate of change of that rate. Okay, so the rate of change of the rate that people are is it entering? Yeah, getting on an escalator. Is decreasing because it's negative. And when you say decreasing, you don't have to say decreasing at a negative whatever. The fact that you said decreasing implies that it's negative. So when we say the rate, it's still just going to be the number. So it's decreasing by a rate of 1/2 people per second squared, because it's people per second, okay, at specifically time 8 seconds. Just realized you can't really see that. There you go. Okay. All right. So that is the end of lesson 4.1. So I'm going to stop this recording and then I will have you go watch the other recording with 4.2. Okay.